So once we start adding our strong base to our weak acid, what's going to happen is our MES, or I'll just write it as HA, our weak acid, and just to be generic here, is going to be reacting with our strong base, with hydroxide. Now what's going to happen is that's going to form H2O and form our conjugate weak base. So we have weak acid that's being transformed into weak base. So we have a solution that's going to have both the leftover weak acid and the weak base that's been formed, and what we have is a buffer. So as we do this titration, we're forming a buffer because we're making a solution that contains the weak acid and its conjugate weak base. So we can treat this like a buffer problem. So ultimately, to find the pH, what's going to be most useful here is to use the Henderson-Hasselbalch equation. Let's make sure I can spell it right. Hasselbalch, as an L in it, there at the end. Right, but again, remembering that this is pH is equal to pKa plus log base 10, concentration of base on the top, and concentration of acid on the bottom. All right, and so we can go through and calculate the moles involved here. Let's imagine we've got 3 milliliters of titrant added. So we could figure out how many millimoles are in that 3 milliliters and then subtract it. There's a slightly different way to do this that's can be easier. You can do it and go through it the other way by calculating millimoles, and you'll get the right answer that way too. But one way to sort of streamline this calculation, make it a little bit simpler, is to recognize that in the Henderson-Hasselbalch equation, we just care about ratios, right? So it's just this ratio between base and acid that matters. So let's think about what's happening here. So HA plus OH minus, this is our reaction that's happening. It goes to A minus plus H2O. So if we imagine that we start initially with one total amount of HA, in this case it actually is 1 exact millimole, but just 1. For adding the hydroxide, we have gone 3/10 of the way to the equivalence point. So, and we'll have 0, and H2O doesn't matter. And so what's going to happen after the reaction is that we're going to lose 3/10 of our HA, all of our hydroxide will react, and then we'll have 3/10 of our A minus. So we can then use the ratio between these values here to get the pH. So pH is equal to pKa, which in this case is 6.27, plus log, my plus got messed up there, plus the log of concentration of base, which is 3/10, divided by 7/10. All right, and that gives us a pH of 5.90. So we see, again, a pretty significant change in pH, but not as drastic, a more significant change than we saw when we had a strong base. So this is our example of looking at something that is before the equivalence point.